Great. So, yeah, maybe I'll just start by welcoming everybody. So welcome back to the final day of the first week. It's Friday today. For those of you in lockdown, it's very easy to get confused about these things. Yes, we're half an hour earlier today. This is our first day with 3 speaker talks. There's 1 or 2 of them throughout the conference. I think everything has been going pretty well so far, so let's just continue like that. We encourage questions throughout the talk, so please do so. Continue doing that. You can do it by either raising your hand on the participants list or typing the question into the chat. And one of the moderators will then interrupt the speaker and invite you to ask your question. It keeps everything moving smoothly. So without further ado, let's welcome back Senthil Todari from MIT, who I hope has had his breakfast. Our speakers we were just commenting today are pretty much all starting at the same local time for them, but we're just getting further and further west as we go along. So Senthil's biography hasn't really changed much since his first talk a couple of days ago. But just in case you weren't there, he did his undergraduate in India before a PhD in Yale, some postdocs, and he's been in MIT since the beginning of the millennium, becoming a full professor there since 2011, and he's an expert in strong correlations and disorder and pretty much anything that can't be captured by traditional Landau theory. And so we very much enjoyed his first introductory talk to neutral Fermi surfaces on Wednesday. He's now going to continue and tell us, I think, about some of the more later results and everything on this. With his talk, Possible Realization and Detection of Neutral Fermi Surfaces. So over to you, Senthil.
Thank you, Sam, and thank you for all of you for tuning in. Those of you who came back, I'm glad to see that you're back. But if not, I'm still glad that you're here. So today I'm going to talk about, so the previous talk was on some basic ideas on the theory of insulators with neutral Fermi surfaces. So today I want to focus primarily on the detection on experiments that can probe a neutral Fermi surface and the possible realization of such a state in some of the materials that I mentioned before. So this is a slide that I showed in the previous talk. So in the last several years, there have been many different kinds of systems that have been suggested, many different kinds of insulating systems that have been suggested to have neutral Fermi surfaces. So weak Mott insulators close to pressure driven or some other way of driving the Mott metal insulator transition have long been suggested to be in states that may have such neutral Fermi surface in the quasi 2-dimensional organic salts, more recently in transition metal dichalcogenides, 1T tantalum disulfide and 1T tantalum diselenide and so on. And most recently in some 2D correlated moire materials, both in moire graphene and in moire and other moire materials. And in the last few years in mixed valence insulators such as ytterbium boron 12, in samarium hexaboride, and in strong Mott insulators with strong spin-orbit coupling, like ytterbium magnesium gallium oxide, sodium ytterbium selenide, and so on. So the summary, the one-line summary of the previous talk is that I argued that there's a presumed low energy theory for such a state with an emerging neutral Fermi surface, that the neutral Fermi surface cannot just emerge as its own, but rather must emerge as part of a package where it's accompanied by a dynamical U1 gauge field to which the neutral fermions are coupled with as charge couples to gauge fields. Okay, so the crucial question is what experiments will reveal such a phase of matter? So that's what most of the talk today will focus on this question. Now, right away, I want to mention something that I think is very important to keep in mind. In detecting phase of matter, it's very important to ask the right question from experiments, right? So there's a very good lesson from history that is worth recalling. You know, ferromagnetism, this the first kind of magnetism that humankind discovered. I gather it was discovered around 600 BC, at least according to Wikipedia. And antiferromagnetism was discovered in the 1930s, but we now know that in materials, antiferromagnetism is actually a more common form of magnetism than ferromagnetism. But despite that, it wasn't discovered for 2,500 years, right? And the reason, of course, is that ferromagnetism is easily detected by, ferromagnets attract various metals. But antiferromagnetism cannot be detected with the same simple probe that detects ferromagnetism. And rather, we need to be able to sense spin orientation with atomic spatial resolution, which was only possible in the 20th century, right? So anybody who tried to look for antiferromagnetism using the same probes that work for ferromagnetism was bound to fail, right? And so the lesson here is that if you're talking about a new phase of matter, you have to tailor your probe to reveal, what the intrinsic properties of that phase of matter, not just hope that the probes that you develop to understand some other phase of matter will naturally reveal what this phase is about. So you often hear statements like, "Oh, spin liquids for experimentalists, it's not very good because there's no, the definition of a spin liquid is that it doesn't have a signal in any of the standard probes." That just means that we had to change our probe and find a probe for which the spin liquid gives a positive signal, right? Okay. So, actually, let me remove this. Yeah. So let me start with some of the physical. I'm going the wrong direction. Let me start with some of the physical properties of this low energy theory. So it's a theory of a Fermi surface coupled to a U1 gauge field. So the rough characterization of the physical properties is the spin physics will be similar to a metal, right? Though of course it's an insulator, right? So the charge physics will be different from that of a metal, but the spin physics, roughly, we might expect that it's the same as that of a metal. So you might imagine that there would be a linear T-specific heat, and that if spin rotation invariance is present, that there is a constant spin susceptibility with a Wilson ratio, the ratio of the gamma of the spin susceptibility to the gamma coefficient being of order 1. And furthermore, the fact that the spin-on excitation is mobile, you might imagine that would lead to a metallic thermal conductivity, kappa going like T at low enough temperature. Now, so all these are true if you ignore the fluctuations of the gauge field. Now, gauge fluctuations will modify these expectations in some way. And particularly, we understand that gauge fluctuations modifies the specific heat at low T into a non-Fermi liquid form. So you should expect to find some deviations. If you could measure the specific heat accurately enough and subtract out all of the contributions, and if this theory is right, you should expect a divergence of the gamma coefficient at low temperature. But it may be subtle to see because heat capacity measurements, as all experimentalists know, are plagued by inclusions from phonons and Schottky anomalies and so on. So subtracting all these different contributions could be different, and you may not be able to resolve the difference between a linear T specific heat and something with a slightly different power of temperature. So if there is a material, there's an insulating material in which you observe these kinds of effects, and most importantly, something like linear T specific heat and metallic thermal transport in an insulator, that will be very strongly suggestive of a neutral Fermi surface. So I want to emphasize that it'll be strong support to hypothesize a neutral Fermi surface state, but it'll at best, it should also be regarded as only suggestive and not a direct proof that there is such a Fermi surface. Okay, so I want to spend a few minutes showing you some of the data, not all of it, but some of it, that really motivates looking into this possibility of a neutral Fermi surface and some materials more closely. Okay, so a number of these candidate materials that I mentioned, the linear T heat capacity is actually seen. So one of the earliest measurements was in this kappa ET organic spin liquid by S. Yamashita et al., collaborating with Kazushi Kanoda. So you see a plot. Actually, I've lost my pointer. Let's see. Maybe I should try to fix it. Okay, yeah. So a plot of C over T versus T squared is a straight line with an intercept that's non-zero, right? So this the slope here reflects contributions from 4 known degrees of freedom, which will go like T, that gives you a T cube contribution to the heat capacity. So the fact that the intercept is non-zero tells you that there's a finite gamma term. And here's a similar looking plot for the other organic material. So it's nicknamed DMIT. The original measurement was again by Yamashita et al. In 2011, but I'm showing you a plot from a more recent paper from Xian Li's group. And here again, you see that the heat capacity has a non-zero intercept as you extrapolate to zero temperature, suggesting a linear T-specific heat. Now, linear T-specific heat is a good thing if it's observed, but this by itself could arise for a variety of reasons. For instance, an Anderson insulator would have a linear T-specific heat. Disorder could often give you linear T-specific heat. So this by itself is not good enough reason. More encouraging is if the linear T heat capacity is accompanied with the metallic thermal conductivity in this insulator, right? So seeing metallic thermal conductivity in an insulator is a spectacular result, right? So naively in an insulator, you expect that nothing moves. Maybe this, if it's magnetically ordered, maybe there's spin waves or something, but those you expect to behave qualitatively, to contribute to heat transport qualitatively in just the same way as, say, phonons or something, some higher power of T. So seeing metallic thermal conductivity is spectacular. So here the experimental story is somewhat confused. There's a very famous experiment from 10 years back by Minoru Yamashita et al. So there's a plot of kappa over T versus T squared, and this DMIT material. And famously, there was an intercept at when extrapolated zero temperature, which implies that this system indeed has metallic thermal transport. Now, the story has become complicated in the last 1 year. So this experiment, there's no published report that reproduced this result, except in the last 1 year when 2 different groups published data on the same material, at least not the same samples, but samples made from the same grower. And you see the results are completely different. So the old experiments are plotted here. This is the Kyoto work of the Kyoto group. And there's one paper from Louis Taillefer's group, in which you see that kappa over T extrapolates to zero, at zero temperature. And another paper from Xian Li's group in Fudan appeared simultaneously, also showing that kappa over T extrapolates to zero at zero temperature. So, so this is concerning, to say the least. experiments on the same system done about 10 years apart give completely different answers. So what should we do, if you're a theorist, right? So the dust needs to settle on this measurement. Hundreds of papers were written based on this data. So to have it overturned after nearly 10 years is a problem. Now, there's one observation about these new results that makes it even more surprising. I don't show it here, but if in first paper, there's a plot of the thermal conductivity out to higher temperature of about 5 Kelvin or so. And the measurements here are already smaller by, by a huge factor compared to the old measurements at high temperature, when you expect that most of the thermal transport is phonon dominated. So this led to some a suggestion that perhaps there's a change in sample quality between these two measurements, and perhaps sample quality depends on how you cool the sample, and maybe they cooled differently and so on and so forth. And there's a new paper by the same group, exploring these differences between these two measurements. So things need to settle down. We'll see how it all ends up. But, there's at least some data stretching back many years that looks very promising that this system perhaps has metallic thermal transport. Now, there's a new system, which is not it's a mixed valence insulator, where again, the results look very encouraging. So this ytterbium boron 12, it's a mixed valence insulator. So here is a plot of the heat capacity divided by temperature versus temperature for two different samples. So the curves are a bit complicated, and this is some reference compound that's used to subtract out phonons and other anomalies, Schottky anomalies. So the main point about this curve is that if you look at the extrapolation to zero temperature, once again, it's a constant, and here's the this number plotted, after subtracting out these other contributions, and you get a reasonable value of the gamma coefficient in this insulator. And this again is accompanied by data from this group, again, the Kyoto group, collaborating with Lou Lee in Michigan. In their two different samples, there is a non-zero kappa over T in the limit of zero temperature. Again, these results should be reproduced by other groups. So any such surprising result, I think it would be wonderful if the experimental community scrutinizes such surprising, interesting results from one group and reproduces them and publishes data that either confirms or does not confirm this finding. As of now, these are the only measurements that are published. Now, the same group had an earlier paper, which is interesting, and it's the observation of quantum oscillations in the resistivity of this material. So there's a plot of the resistivity. So it turns out this material is very much, is somewhat similar in its transport to, the temperature dependence is similar to samarium hexaboride, where it increases rapidly as you decrease the temperature before saturating to at a high value at low temperature. So here, likewise, it saturates, it's insulating down to 2 Kelvin or so, and then it saturates at some at some high value of the resistance, resistivity at below that temperature. And if you measure the resistivity as a function of magnetic field, it comes down a little bit by a factor of 3 or so. But just before it dies off, above 40 Tesla, there's some wiggles that are seen. And the authors argue that these wiggles have a nice periodicity with 1 over the magnetic field, and that represents Shubnikov-de Haas oscillation. And this is plotted at various angles, and you can see maybe 4 oscillations here at this angle. Not that many, but it's still interesting that you see anything like a Shubnikov-de-Haas oscillation in an insulator. So there are other intriguing observations in the same paper, but once again, these kinds of results need to be corroborated by other groups. There is one other paper by Suchitra Sebastian on quorum oscillations in the same material, but unfortunately with rather different looking frequencies. So in any case, the experiments need to settle down. There are all kinds of things that are debated in the experimental community on what's going on. In the sister compound, samarium hexaboride, as many of the experimentalists probably know, people debate issues like, is there aluminum flux in this material and things of that sort. But I'm a theorist, so I'm going to sort of step back from these controversies and say, look, there are interesting looking results, and these results motivate looking closely at the theory of insulators with neutral Fermi surfaces and asking, A, understanding the theory, and B, asking, what sort of experiments will help unambiguously establish the presence of such neutral Fermi surface.
Senthil, there's a question from Gang Chen.
Yeah.
Are there any thermal Hall transports in ytterbium boron 12 and samarium hexaboride?
So I'm not aware in samarium hexaboride, but in ytterbium boron 12, they sought to find a thermal Hall signal, and they could not, out to 12 Tesla feet. So I should emphasize that the quorum oscillations are seen above 40 Tesla, but the heat capacity and the thermal transport measurements have so far, at least in the published data, only been done up to 12 Tesla. And up to 12 Tesla, there is no thermal Hall signal. Okay. Other questions?
There is another question from Pavel Volkov, who asks, what is the theoretical expected for the effect of disorder on a neutral Fermi surface coupled to a gauge field?
So I'm not good at this in the talk, but I can tell you what I know. So zeroth order disorder will give you a finite elastic scattering rate for the spinons, which will lead, and indeed that's taken into account in this prediction that the thermal conductivity will be linear in temperature. If coming purely from an elastic scattering, the thermal conductivity actually has a non-Fermi liquid temperature dependence, but we don't expect that that's going to be the dominant effect in the presence of impurities. Now, with stronger impurities, you will localize the spinons and get rid of the thermal conductivity, right? But, so if the material is reasonably clean so that you can talk about a Fermi surface, then it's not that different from a metal with a Fermi surface. There'll be a diffusion of spinons, and the zeroth order, that's what happens. Okay. I see that there's one more question.
Yes, the final question is from Liang Wu, who asks, does ytterbium boron 6 also show a metal insulator transition as a function of temperature? So ytterbium boron 12.
Yeah, so ytterbium boron 12 does not, as far as I know, show a metal insulator transition as a function of temperature.
Okay, I don't see any more questions for now. So,
all right, so let's move on. So I'm going to, stop talking about experiments that have already been done and talk about what experiments can be done in the future to help us, attack the question of whether or not there's neutral Fermi surface by doing different kinds of experiments. So, people think they may have direct detection of dark matter. So let's ask about direct detection of neutral Fermi surface, right? So there's a number of different ideas that have been proposed over the years that I want to go through for detecting such a Fermi surface. So the first idea is to look for fetal oscillations. So let me explain the theory and some proposed experiments that will probe fatal oscillation with a neutral Fermi surface. Okay,
Okay,
so the normal metal.
There's one more question came up in the chat, which was, do we expect quantum oscillations in neutral Fermi surfaces given that they don't couple to the physical magnetic field?
Yes, so that is something I'm going to talk about at some length. Okay, so but first let me talk about fatal oscillations. So in a normal metal, the sharpness of the Fermi surface leads to oscillations of the charge density around impurities. So that's the phenomenon known as fatal oscillations. And this is related to singularities in the response function in both the charge channel, in the charge channel at the 2kF wave vectors of the Fermi surface. There's of course also a related 2kF singularity in the spin density response. Now, so the claim is that the sharp neutral Fermi surface also leads to 2kF singularities in both the spin and the charge response. So for the spin response, it's perhaps a no-brainer. After all, you know, the spin physics you expect is not that much modified from that of the metal. But, you know, why would you imagine that there's a charge fatal oscillation in an insulator at all, even if it has neutral Fermi surface? Okay, so let me explain that. So the point is that the charge density correlations at short distance, they couple to the density of spin-ons, right? The spin-on density correlation. So the spin-on density is F dagger F. It is distinct from the spin density, which is F dagger sigma F. So this the this in the triplet channel, while this is in the singlet channel. So symmetry-wise, this object has no distinction. It has the same symmetry as the charge density. So there's naturally a coupling between the charge density and this object. Now it turns out, and this is what comes out of the theory of this state of matter, the coupling of the spin onto the gauge fields ensures that the mixing of this operator with the charge density vanishes at long wavelengths as Q goes to 0. But at short wavelengths, this gauge field does nothing, and it doesn't prevent any mixing between the spin-on density and the charge density. Okay, so one way of thinking about the spin-on density is that it's related in the spin system to a dimer type correlator, to a dimer type order. So it modulates the spin-on kinetic energy, and therefore, you know, a dimer type distortion you would imagine will show up in charge density correlations. So the sharpness of the spin-on Fermi surface means that there'll be sharp 2kF structure in the spin-on density correlations, and hence you'll have sharp 2kF singularities in the charge density correlations in the smart insulator. So you can estimate the magnitude of this within mean field theory, and the effect is most observable in a weak Mott insulator, and it turns out the magnitude is more or less unchanged across the Mott transition. But correlation will, of course, reduce it compared to the free Fermi gas, and within the mean field, you can estimate this reduction and so on and so forth. Now, directly detecting charge fatal oscillations is hard, even in a metal. You need to emit charge density variations on the scale of the Fermi wavelength, which is extremely hard. But you know, people get at the same physics through other probes, and similar other probes will be useful for us here. So there's two proposals to detect related phenomena that we came up with. So the first is that so this spin-on Fermi surface will lead to a cone anomaly in the phonon spectrum. Now, let me remind you what the cone anomaly is. It's a sharp structure in the phonon dispersion or phonon lifetime at phonon wave vector, which matches any of the 2kF wave vectors of the Fermi surface in a metal. Right? So Kohn argued that the shape of the Fermi surface will have a fingerprint on the phonon spectrum in a metal. And so what I'm going to argue now is that the same story will be true in an insulator with neutral Fermi surface, that the neutral Fermi surface will have an imprint on the phonon spectrum. So the other experiment is to do STM, and I'll talk about that later. But first, let me describe the Kohn anomaly. So let's begin with a qualitative understanding of why there's a cone anomaly in a normal metal. So the way phonons are understood in a normal metal is that phonons, of course, have to do with the ionic motion, but the ions carry charge. And the theory of the phonon dispersion in a metal is strongly affected by how the ionic motion is screened by, use the immortal words of Ashcroft and Merman, by the nimble electron sea. The electrons move rapidly and screen out the Coulomb interaction, the Coulomb electric field coming from the motion of the ions, and that's what determines phonon dispersion. Now, as the phonon momentum goes past 2kF, there's a change in the ability of the electron sea to screen the ionic motion, and that abrupt change of the screening leads to the cone anomaly. Okay, so that's the standard story. So now let's think about the spin liquid Morton-Slater. So I described this picture where the ions are rendered neutral by the holon, which is stripped off from the electron, by the holon attaching itself to the ion to form a neutral entity. And then the spin-on is sort of swimming around freely, right? So it might seem as though as the entity that's moving in a phonon is this combined ion plus holon object, which is electrically neutral. So it might seem that there's no long-range Coulomb forces to screen, but that's not true, because even though the ordinary electrical field no longer exists when this entity moves, there's an internal gate charge that's carried by the holon that's not carried by the ion. So this entity carries internal gate charge of +1. And so this internal electric fields that have to be screened, and they are screened by the nimble spin-on fluid, and the change in the ability of the spin-ons to screen these internal electric fields leads to a cone anomaly as Q goes through 2kF in this spin-on Fermi surface state. So based on this picture, you then expect that indeed that the cone anomaly will be there in such an insulator, right? So the 2kF wave vectors are often known. They're known for both organics, and they're known for various other weak Morton insulators. They're more or less the same, unchanged from the proximate metal. The phonon spectrum can, of course, be obtained, maybe not for the organics. In the organics, perhaps through an elastic X-ray or something, but in other systems through either neutron or X-ray. So I think it'd be very interesting to look for cone anomalies in various insulators that are suggested to have neutral Fermi surfaces. Now, this cone anomaly survives even in a strong Morton insulator if it has a Fermi surface, if it has a spin-on Fermi surface. And in general, what this argument in the previous slide tells us, I'm going in the wrong direction. No. Oops. Yeah, it's basically that you expect that the spin-on phonon coupling is not that different from the electron phonon coupling. And indeed, this the phonon dynamics may actually be a useful probe of spin-on physics in a gapless spin liquid Morton insulator. For instance, sound attenuation or other such experiments are predicted to be not that much different from what it is in a metal. Okay, so that's one kind of probe. Now, the other kind of probe that I want to talk about is to do STM, scanning tunneling microscopy. Now, the tunneling conductance is proportional to the single particle density of states. The tunneling conductance at some bias is proportional to the single particle density of states at that same bias. Now, tunneling here, first of all, we should expect that since it's an insulator, there's a tunneling gap, right? So there will be a gap of delta in this tunneling density of states. So tunneling requires injecting both the gap charge and the gapless spin-on into the system. So the tunneling density of states will be given by a convolution of the holon and spin-on density of states. So within the mean field, you can work this out. And apart from a gap, there'll be some onset at a threshold. turns out that in mean field, this onset is linear, and that will be modified by these fluctuations. But what I want to focus on.
There is a question from Gautam Nambia.
Yeah, go ahead.
Sorry, I have a naive question. Does the picture you showed on the previous slide require deviations from half filling? Like at exact half filling, can we still see what you showed?
Oh, absolutely. In fact, I was talking about exact half filling.
But then there are no more. There's no charge degree of freedom left anymore, right?
So in a strong, you're in a strong motor insulator, right? If you just describe it by a spin model, that's true. But in a weak motor insulator, where there's the charge correlation length is not zero, right? But it's finite, right?
Okay.
So then the short distance charge fluctuation, there's just no long wavelength charge fluctuations.
Okay. Well,
okay. Of course, in a spin model, there's no charge fluctuation, but a spin model is an approximation to a better model, to something like a Hubbard model, which has both charge and spin fluctuations.
Okay.
And the same is true even here. If in a spin model, of course, you can't tunnel electrons in, right? But a spin model is an approximation to reality. Okay? In the real model, there is a charge gap, and there are charge excitations, right?
Yeah.
So the behavior near threshold is determined. The onset near threshold is sensitive to the density of states of the spin-ons, right? So let me sort of repeat this story. So the slope of this onset is what I'm calling A, and this A is proportional to the spin-on density of states at the Fermi surface. Now, near defects, this A will have a spatial dependence that comes from the physics of Fetal Oscillations. And these modulations will be a 2kF wave vectors with the spin-on Fermi surface. And correspondingly, there'll be a standing wave pattern, which will lead to a spatial modulation of A at near threshold, right? So if you park your bias just near threshold and see how the tunneling conductance oscillates as a function of position, that oscillation will contain information, will be a direct map of the 2kF wave vectors of the spin-on Fermi surface. So these kinds of experiments are routinely done in metals or superconductors, where this effect is known as quasi-particle interference. Probably familiar to many people that are listening in. So what I'm talking about here is an example where we see that what's usually called the quasi-particle interference signal does not actually require quasi-particles. And here, we have the same signal, but in a system without quasi-particles, right? So perhaps the name is misleading, but in any case, this QPI signal in this system, there will be a QPI signal near onset, and that can be used to probe the spin-on Fermi surface. This experiment is not very suitable for a strong insulator because then it's very hard to tunnel in. But for a weak insulator at not too low temperature, it will presumably be possible to tunnel in. And it may be particularly well suited to 2D materials and to the Moiré systems. Now, there's another idea. It's a very interesting idea, though it's a very hard experiment by Mike Norman and his collaborator, Miklitz, several years back. That's to do a GMR type experiment where you separate two ferromagnetic materials through a spin liquid buffer. And the spin liquid, if it has a gapless spin-on Fermi surface, will lead to RKKY coupling between these two ferromagnets. And so as you change the thickness of the spin liquid buffer, you will see oscillating magnetic coupling between these two ferromagnets, which perhaps you could detect. So this would be a straightforward, if this works, it'll be a very clean demonstration. The problem is that you need to control, since this oscillation occurs on the OKKY, oscillates on the scale of the Fermi wavelength, you need to control the spin liquid layer, its thickness, with atomic precision. Now, once again, in a 2D material, maybe this kind of thing is possible by playing around with gates and so on to very clearly define the spin liquid region. So in some of the materials that are currently being discussed, this experiment may actually be feasible, but we'll have to see. Okay, so that's about, so fetal oscillation is one set of phenomena that one could use. So next I want to talk about various effects associated with the magnetic field. So let me just launch into it. So the most interesting phenomenon is that an external orbital magnetic field applied to such a system induces an internal magnetic field that is seen by the neutral fermions. Okay, and the physical reason why this happens is that the external magnetic field couples directly only to the holon, right? The holons are the only things that carry external electric charge into the external electromagnetic field. But the response of the holon has some diamagnetic response to the external magnetic field. So the holons also couple to the internal gauge field. So the internal gauge field sets up its own magnetic field in response to the external magnetic field. And the resulting internal magnetic field is then sensed by the spin-ons. And so effectively, the spin-ons sense a part of the external magnetic field. So for small external fields, we expect that the internal magnetic field will be proportional to the external field. The coefficient of proportionality, it's hard to calculate very accurately, but the qualitative picture for what happens as you go through the metal insulator transition is this. In the metal, of course, alpha is 1. As you go into the insulator, alpha will start decreasing from 1 in some way and become very small if you're deep inside the insulator, right? So if you're in a weak water insulator, somewhere in this region, you expect to find some internal magnetic field that is a fraction of the external magnetic field, okay? So there's many consequences of this statement. The first is that there will be, in general, a non-zero thermal Hall effect at weak fields. So again, just like in a metal, whether there's a Hall effect or not depends on whether it's an ordinary metal, a compensated semi-metal, things of that sort. So all the same statements about the Hall signal that apply in a metal also apply here. There'll be the Hurst-Van Alphen oscillations with frequencies of order the conduction electron Fermi surface orbits. And again, let me emphasize that these effects are likely only visible near the metal insulator transition, but already on the insulating side, but not far away from the metal insulator transition. Okay. Now let me talk about Shubnikov-de Haas. So what I'm going to argue is that it is possible for there to be Shubnikov-de Haas oscillations in such an insulator if the conditions are right, right? So the total electrical transport in such a system where there's a neutral Fermi surface coupled to a U1 gauge field, the total resistivity is determined by a rule that was derived in the 1980s for such a system, in very early, beautiful work by Levi-Orfe and Anatoly Larkin. I'll give a simple-minded explanation of this in a couple of slides. But for now, let me just state the result. And the result is that both the bosons, the holons, and the fermions contribute to the total resistivity, but they contribute in series. Right? It's not like, given that there's two sets of degrees of freedom, they act as parallel conducting channels, but rather they act as conducting channels in series. Okay, so the boson resistivity adds to the fermion resistivity. Now the entire system is insulating because remember the way we constructed this insulator was by saying that the holons are gap. The holons have formed an insulator, while the fermions have formed the spinons have formed a metal, right? So in the neutral Fermi surface insulator, this contribution is finite, but this contribution is infinity, and so the net result is an insulator, okay? But this contribution is infinity only at 0 temperature. At small but non-zero temperature, this contribution is large and is increasing as you decrease the temperature, and in an ideal clean system, it will have some activated form. Now in a magnetic field, the boson contribution will more or less be, this insulating behavior will indeed be more or less unaffected by the magnetic field. But the spin-on contribution, because the spin-on sense apart to the external magnetic field is an orbital field, the spin-on contribution will show Shubnikov-Dihas oscillations, okay? And since these two add in series, the net result will be that you have a temperature dependence that is thermally activated, but on top of that thermally activated temperature dependent resistivity, there will be a small piece that shows quantum oscillations that are periodic in one over the external field, right? So this effect may be observable as a small oscillation on top of an activated background, okay? So again, as usual, there are many caveats. The system needs to be clean enough to see these quantum oscillations of rho chi, and it needs to be not so resistive that this background contribution completely overwhelms the small contribution. So if everything works, you may be able to see such Shubnikov-Dihas oscillations in this insulator, okay? Now, one of the questions that people always ask bring up is a puzzle about this response. How can a neutral Fermi surface not respond to a static electric field, but respond to a static magnetic field, right? To a static electric field, it behaves like an insulator, right? But then how can it show quantum oscillations in a static magnetic field? So within this, so this theory of this neutral Fermi surface, this entire package of neutral Fermi surface plus U1 gauge field gives a very concrete and definitive answer to this question, which is what I want to describe. And in that process, they also give an understanding of where the CFA lock-in rule comes from. So we can see this difference between static electric and magnetic fields for various physical quantities already within linear response, right? So the holon couples both to the external electromagnetic field and to the internal, to the dynamical U1 gauge field. So the net gauge field that the holon sees is capital A minus little a, while the neutral fermion only couples to the internal gauge field, right? It has no minimal coupling, no direct coupling to the external gauge field. That's why we call it neutral. Now the holon current in response to these, both these gauge fields, there'll be some response function KB times capital A minus little a, while the neutral fermion will only respond to the little a field and will have its own response function K psi. Now the condition of gauge invariance is invariance with respect to this internal gauge transformation is that the holon current is equal to the fermion current, to the spin-on current, okay? So the gauge theory at long wavelengths, the net gauge current should be 0. So this means we must equate these two things to each other, and equating these two things to each other enables us to figure out how much little a is induced in response to an external capital A, right? So equating these two gives us an equation that we can solve for little a in terms of capital A, and solving that gives you this equation. So given a capital A, this how much internal A that you induce. Now, KB and K psi are both functions of frequency and momentum. And the crucial point is that the ratio that appears here has different limits depending on whether we take the momentum going to 0 limit first or the frequency going to 0 limit first. Now, this statement about the response functions depending on order of limits between frequency and momentum It's a very familiar statement about a Fermi gas or a Fermi liquid. And a similar kind of dependence on order of limits applies to this ratio. And if you take the limit of Q equals 0 first, and then omega going to 0, which is what's important to ask whether the system is an insulator or a metal. So then in that limit, this ratio, you can calculate it, and it goes to 0. So for an external electric field, then the induced electric field is 0. And so the spin-ons don't couple at all to the static external electric field. Now you turn on a static magnetic field, 0 frequency, and then take the limit of Q going to 0. Then it turns out that this number goes to a constant, and this constant is simply related to the diamagnetic susceptibilities of both the holon and the spin-on, which are both finite numbers, even when the holon is in an insulator, right? So there's some number here, which is a constant. So consequently, this alpha that I introduced is just related to the ratio of the diamagnetic susceptibilities of the gap holon and the gapless spin-on. So consequently, there's a non-zero internal magnetic field that's induced in response to a static external field. And so the system is allowed to have different behavior for static electric and static magnetic fields. Okay?
Hi,
There's a
Senthil,
So that's
question in
the
the chat.
solution of the puzzle.
Okay,
Sure.
yeah, there's a question from Gautam who says, can you just explain a bit more why JB has to equal J psi? And he says, in particular, in the strong Mott limit, since JB is 0, is J psi also 0? On the previous slide.
Oh, very good. Yeah, so let's see. Yeah, so this entire story is only relevant to a weak Mott insulator, or at least to any Mott insulator where there is still some charge fluctuation, right? If you really are interested only in thinking about a spin system, right? In the pure spin system limit, you need to invoke a different mechanism for an orbital coupling of the magnetic field, which could happen in some materials through a completely different mechanism that I've not talked about here, right? But let's ignore that. This mechanism will give you zero coupling if you have a pure spin model that did not descend from a Hubbard model, okay? So we're always going to work in a Hubbard model type description, and a weak Mott insulator, or if you're close to a metal insulator transition, even if you're not in a, let's say, a mixed valence system close to a metal insulator transition, it's appropriate to keep the gap charge degrees of freedom. And then the full gauge theory involves both charge and spin contributions. And the point is that even though the charge is gapped, it can affect the low energy physics by indirectly by affecting, because it's coupled to the gapless internal gauge degrees of freedom. Now, as to this condition, perhaps it's easiest to see by writing down a Maxwell equation in any gauge theory. If you write down in any U1 gauge theory, if you write down Maxwell equations and take the long wavelength limit, the net gauge current or gauge charge density has got to be equal to 0. You can't have unscreened currents because they give rise to long-range effects in the Q going to in the long wavelength limit in any gauge theory. It is very easy to see for the charge density for the time component of this equation. Now that means it's unscreened gauge charge, which leads to electric fields that go off to infinity. Right? So the equation divergence E equals 4 pi rho, 2 pi rho guarantees that as Q goes to 0, rho is 0.
Okay, thanks.
Other questions?
I don't see any more just now.
All right, so let's move on. So the next effect I want to talk about is discussed in a nice recent paper by Senthil Todari and his collaborator. And it relies on an old observation that goes back to Taika Ng and Patrick Lee from 2007. So though the DC conductivity is 0, if you go to non-zero frequencies, there'll be some weak power law AC conductivity in an insulator with neutral from the surface, right? So, so the real part of the conductivity, so in an ordinary insulator, there'd be a gap, and then there'd be some absorption above the gap. But then if there's neutral Fermi surface, there'll be a tail that leaks in below the nominal gap. So the subgap absorption, and it really comes from what I just described in the previous slide. It's only in the strict omega going to zero limit that this internal field is zero. At non-zero frequency, there'll be a suppressed internal electric field that's induced, and that'll then lead to some absorption of power by the neutral Fermi surface. Okay, so there is some subgap absorption. Now, if you go to non-zero frequencies, and then you turn on a static magnetic field, an ordinary metal has a cyclotron resonance that shows up as a series of peaks at the cyclotron frequency. Now, what's argued in this paper is that a generic spin-on band, not some idealized thing, but a generic spin-on band, will have cyclotron resonances. So this subgap absorption will have cyclotron peaks that occur at various frequencies. The theory is a bit more, the details are a bit more complicated to interpret than the normal metal, and it requires some theory. But nevertheless, there will be cyclotron peaks, which again are a signature, can be used combined with some theoretical modeling to provide some information on the structure of the spin-on Fermi surface. So this again may be a doable experiment in some of these materials in the future. So next thing I want to talk about very briefly is photo emission. Again, it's an insulator, so photo emission is a bit hard, but if weak insulator, perhaps not entirely impossible. And this was discussed in this paper from a few years back.
Before you go on to this, I think there's a question. Yashar?
Yeah.
So I just want to see if there is a distinction between a system which are weakly localized with some localization length. So in this kind of systems, there is no percolation or there is no DC conductivity. But if I have a strong enough magnetic field, I can cycle electrons and I would see magnetic oscillations, or I would see AC conductivity or photo emission. So is there a distinction between this spin liquid with neutral Fermi surface and weakly localized metals or weakly localized insulators?
A weakly localized insulator, you mean in the regime in which you basically have diffusive electrons with small weak localization corrections? That's exactly. A metal, right? That should be called a weakly localized metal.
But a system where electrons cannot, there is no DC conductivity, but I have some with any finite temperature or any, I would see a very high resistivity for the DC conductivity, for a DC transport. So in this
right. So you're either in the Anderson insulator, deep in the Anderson insulator, or you're in a regime of temperatures in which you haven't yet seen strong localization effects. So if you're in a regime of temperature in which the localization effects are only weak, you're still in a diffusive regime, a metallic regime, right? While here, remember the resistivity, at least in the ideal limit, is activated, right? It's really shooting off. It's becoming an insulator.
But then let me put it this way: if I don't have percolation in my sample, so that I have some puddles right here and there, and they cannot make it from one end of the sample to the other, I would not see DC conductivity. But all the other effects that you mentioned, like a magnetic oscillations or AC conductivity.
No, good. So this, of course, is an issue that anytime anybody sees quantum oscillations in an insulator, the first thing that everybody should ask the experimentalists is whether they have metallic puddles inside their sample, right? And of course, metallic puddles that don't percolate can give you quantum oscillations. But so some of the effects that I described will not be seen. So if you can do STM, right? STM can definitely tell, because it has spatial resolution, can definitely tell whether or not it's metallic puddles or the system is reasonably homogeneous, right? So, so those are the kinds of things that experimentalists have to sort out, and it's no single experiment is going to be definitive proof. I think depending on the system, one will have to use a combination of experiments, to make the case, right? Okay.
Thank you.
Sure.
Okay,
So photo emission.
Just to say, you have about 15 minutes left, including some time for questions.
Okay, very good. So I'll keep going, and then then it's time for me. Whenever you deem fit for me to stop, I can just stop. Okay. So so in an insulator, there is a gap delta to add or remove an electron. Now, there's something that in the tube literature, the photo emission community spent emphasize that there they were talking about the superconducting state, but nevertheless, we'll use that here. The locus of minimum gap excitations, theoretically here, will track the neutral Fermi surface, and this is something that can potentially be measured in ORPIS. So the electron spectral function on the electron removal side has a gap, and then some threshold, and there's an onset. Now, if you look at the momentum at various cuts in energy through here, the momentum at which this onset happens will be centered on a ring that's determined by the neutral Fermi surface, and this ring will broaden out as you increase the energy into a sliver whose width will be determined by the frequency, by delta K. Right? So this, if photo emission could be done, this is potentially a way to measure the Fermi surface. And this again may be feasible in some of the systems, but not all. So that's all I'm going to say about photo emission. So finally, let me turn to magnetic neutron scattering. Now, neutron scattering, is a powerful probe of spin correlations, and sometimes people say that for any spin system in any water insulator in any phase whatsoever, unless you can probe it through neutron scattering, you don't really know what's going on. So I want to push back on that notion, and I want to say, with some apologies to my neutron scattering friends who may be listening, that if what you have is a neutral Fermi surface state, that neutron scattering is less directly useful to detect the neutral Fermi surface. The spin correlations are expected to be similar to a metal. So what you would expect, it's going to be at least as hard as detecting the Fermi surface of a metal by doing neutron scattering. Right? What you expect to see is broad continuum scattering, the standard picture of a Lindard type response with weight in this area. And perhaps there's some collective mode, some spin zero sound or something like that. You may be able to see this onset here. And some details of the continuum can give some indirect and possibly useful evidence, and you can try to make a case, but it's likely to be confusing and controversial. The most convincing measurement would be a measurement of this 2kF cutoff of the spectral weight. So if that can be done, that would be extremely useful. But in the absence of that measurement, I think just seeing broad continuum scattering, it's hard to convince oneself that what one is really seeing is a spin-on Fermi surface. Okay, so that's the comment about neutron scattering. So now, before I close, let me very briefly talk about what I think is a really exciting possibility for neutral Fermi surface states, and actually for a lot of other things in condensed matter physics. And it's in this world of Moire materials that has opened up, of correlated Moire materials that's opened up in the last couple of years. Okay. So I guess everyone in the planet who's interested in condensed matter physics has heard of these Moire superlattices. So the standard example is twisted bilayer graphene. But apart from twisted bilayer graphene, there's a number of other Moire materials that people have studied, and all kinds of amazing things have been found. There's the magic angle twisted bilayer graphene, and then you can further align it with the boron nitride substrate and find ferromagnetism. There's a trilayer graphene variety, which when aligned with boron nitride gives rise to long period moire structure and the twisted double bilayer graphene and so on and so forth. So I'm going to focus on this example, though some of what I say applies to other moire materials as well. So in the context of this talk, this ABC stacked trilayer graphene on boron nitride is particularly interesting because this group in Berkeley, led by Feng Wang, showed that you get gate tunable Mott insulators in this system. Okay, so so this structure, ABC stacked trilayer graphene, is aligned with the boron nitride substrate and encapsulated by two gates, one at the bottom and one at the top. And by controlling both the bottom gate and the top gate, you can both control the charge density of the moire layers, but also control a perpendicular electric field D. Now, in this plot, moving in this direction tunes the electron density, and moving in this direction tunes the perpendicular electric field. So charge neutrality is this bright line. And the thing that I want to draw attention to is half filling of the moire band, which is here, or quarter filling. Now, amazingly enough, it turns out that in this structure, the bandwidth of these moire bands is controlled by D, where the Coulomb interaction strength, so you can think of that as a Hubbard U, is independent of D. This means that you have an electrically tunable knob to continuously tune the strength of correlation effects, to tune the strength of U over W. And here you see what happens at these fillings is that at zero displacement field, they are metallic. But as you march up in displacement field, what happened? As you march up in displacement field, you go from a metal to an insulator. And this metal to correlated insulator transition is induced just by changing gates, right? So it's wonderful for all of us interested in strong correlation physics. We can tune in and out of the metal insulator transition either at fixed density by changing the bandwidth, or we can dope out of the Mott insulator very easily with gates, okay? Now, if you focus on commensurate partial band fillings with integer number of electrons per moire height, in the weak interaction limit, you get a Fermi liquid, while in the strong interaction limit, we can argue that, so this is a story that I'm not going to worry about in this talk. You can argue that the ground state will have ferromagnetic order, but instead I want to focus on the weak Mott insulator. After all, in this system, we can tune as close to the Mott transition as we want. So in this regime, based on analogy with the usual triangular lattice Hubbard model, we might imagine that this is a right platform to see a quantum spin or spin valley liquid with a neutral Fermi surface. So there's various possibilities for the evolution of the phase diagram as a function of bandwidth over W. And so this is the possibility that we are interested in the context of this talk. And one feature of this system is that even though you can tune parameters very easily, the kind of experiments you can do, the most reliable experiments you can do currently are electrical transport experiments. You may be able to do some STM, but not fully, the full power has not been developed yet. But so can we distinguish these different things with purely electrical transport? And it turns out that the answer is yes. So what is feasible to do experimentally is to study the electrical resistivity as a function of temperature and displacement field. Now the insulator is not a spin liquid, then the Mott transition is likely first order, and there'll be hysteresis. And by studying the shape of the first order line at non-zero temperature, we can learn something about the correlated insulator. With what direction does this first order line curve? That will tell us something about the entropy of the insulator relative to the metal. Now, the most interesting possibility is that I said in an earlier slide on Wednesday that the neutral Fermi surface state admits a continuous Mott transition with distinctive transport signatures. So if you tune close to the Mott transition, the first thing you can do is to look for quantum oscillations with resistivity, and perhaps you'll see that. But the other thing you can do is to look for these transport signatures. So probably out of time, so let me just tell you what the signature is and skip the explanation. The signature is that the residual resistivity, as you approach the transition, the mode transition from the metal, so the zero temperature resistivity will be a constant in the metal. And right at the transition, it will have a universal jump that's of order h over e squared with a coefficient that's of order 1 in front of h over e squared. So let me finish by showing you the finite temperature plot. So perhaps this is the most useful plot for experimentalists. The resistivity as function of temperature. In the metal, it looks like this. In the insulator, it looks like this. It goes upwards. And right at the mode quantum critical point, it looks like this. So if you look at the residual resistivity, there's a jump, which is of order h over e squared. And there's some scaling plot that you can make, that you can attempt to make of this behavior. And this kind of scaling plot is presumably feasible in this system, where you can easily control, tune through this, where this tuning parameter delta is just the difference between top gate and bottom gate voltages. So let me skip this slide. There are other platforms, and then spin transport may be measurable. So let me summarize the story. So the main thing I want to emphasize is that an insulator with the neutral Fermi surface is allowed to exist theoretically. We know how a natural description of such a state, and we know how it will reveal itself in diverse probes. And it gives us some optimism that at least in some of these experiments, it's not crazy to contemplate that something like this may actually be going on. So finally, my collaborators most recently on this topic have been two former postdocs at MIT, the Banjan Chaudhary and M.T. Soderman, and a former student, Jahi Zhang, who all left now. And thanks to Patrick Lee for many conversations over the years, and particularly to all the experimentalists who have chatted with in recent years. So thank you.
So thank you, Senthil. Should we unmute and... Okay, so the program is a little tighter today because of 3 talks, but we have 5 to 10 minutes for some questions. So the first question, I think, was from Pavel Volkov. Pavel, do you want to unmute and just ask your question?
Yeah, sure. So my question was about the strength of interaction between spin-ons. What microscopic and how do the microscopic parameters of, for example, Hubbard model control the interspin-on interactions? And in particular, for a weak mode insulator, can we really treat spin-ons as being weakly interacting, weakly correlated fermions?
For universal properties, the dominant interaction between the spin-ons comes from their coupling to the gauge field, right? And the spin-ons couple to the gauge field with strength 1. And the question you can ask is how important are these gauge field interactions at in the low, in the low energy limit. And I don't recall if you were had a chance to attend the talk on Wednesday, but what I emphasized is that the spin-on gauge field problem is a strongly interacting problem. So it's certainly not correct at in the deep infrared limit to treat the spin-ons as free. They're not good quasiparticles. They are scattered strongly by the gauge fluctuations. And we have some reasonable, the statement I believe I used is that we have a reasonable first draft of how the spin-on, the spin-ons that are strongly coupled to the gauge field, we have a first draft understanding of how this system behaves in the low energy limit. Okay, so for instance, there's various non-Fermi liquid features that we have a reasonable sense for how to calculate, at least approximately, if not completely accurately.
Thank you.
Okay, so the next question I think is from Marie-Theresa Hubsch.
Yeah, hi, thank you. So I was wondering whether it's possible to use the magneto-optical Kerr effect So if you have some magnet and then put neutral firmness material as a layer on it, then maybe the magneto-optical Kerr effect could show the same properties of the magnetic layer, right? Because it's transported through RKKY.
That sounds very
Interaction.
interesting. It's just that I'm not sure I know what the magneto-optical Kerr effect is. So I'm familiar with the polar Kerr effect. Is that but that's not what you're talking about, right?
So just some like linear polarized photon onto the surface, and then the polarization gets a Kerr angle due to the.
But is this in the reflected light or in the transmitted?
Yeah, in the reflected. Yeah.
In the reflected light in a magnetic field.
No magnetic field, just the interaction with the magnetization of the of the material. Maybe it's more of a surface effect. So maybe that hinders. Maybe that's an obstacle. Yeah, I don't know.
No, so the thing I should emphasize is that the state that I've described doesn't have a magnetization. It has magnetic fluctuations, but no magnetization.
Yeah, but through, like, if you have a magnetic layer and then on top you have this neutral Fermi surface layer, then
I see.
through RKKY interaction, the same properties should be propagated, right?
No, so to understand, you're saying put a ferromagnet and on top of that put the presumed material with a neutral spin-on Fermi surface. And if you can again control this Fermi, the insulator thickness with atomic precision, and then see how the induced magnetization of the top surface varies as a function of thickness by studying the Kerr effect.
Yeah, and maybe it's easier because there's no sandwich necessary, right? You can vary the thickness much more easily.
Right. So if you could make layers of this material with if you could make this insulating material with atomic precision, then yes, I think that there would be a signal. But it's tough, right? You have to compare different devices that you make with different thicknesses, and there's a way to control the thickness in situ that may be preferable.
Thank you.
Okay, thanks. So in view of time, we'll take these last two questions, but could you try and make them as quick as you can? We can continue the discussion later if needed, and then we'll have a short break before the next talk. So Yashar?
Yeah, so thank you for the talk. My question is about this continuous mode transition. Can you elaborate a little bit? What do I need in this material to have continuous versus second order versus first order transition?
What do you need?
I mean, which kind of, I mean, does the interaction have to be different, or is there a risk?
No, so the statement is that spin liquid with a neutral Fermi surface admits a continuous mode transition, which you can analyze and calculate all the universal properties of. Now, I think you're asking, or maybe, so one thing you could be asking, let me give you two interpretations of your question. You could ask, what does it take to get such a neutral Fermi surface state as opposed to, say, an antiferromagnet, right? So that, of course, depends on microscopics, and one has to have a reliable way of calculating the microscopic phase diagram. Now, for these materials, the model, at least for this ABC trilayer on HBN with one sign of the displacement field, we do have a microscopic spin valley Hubbard model. So the way to do that calculation would be to do DMRG on strips and try to extract out an answer. It's very hard because of many degrees of freedom. but hopefully somebody will do such a calculation in the near future, right? But short of doing a microscopic calculation, we can't answer that question.
But DMFT cannot capture these effects, right?
Oh, these spin liquid phases are beyond DMFT. They have long range entanglement. That is beyond conventional DMFT. There may be some clever way to do DMFT. So DMFT will completely miss any spin liquids.
Thank you.
Sure.
Okay, then one final question from Gang Chen.
So I have a rather quick question because of time. So this Maury system, for when you talk about this Harvard model, in a strong coupling limit where there are more degrees of freedom, is that obvious it's some kind of ferromagnetic due to flat band system?
Yeah, so,
right?
So I think you're asking about this statement, are you?
Yeah, I'm asking whether it's, I'm asking this statement, yes.
Yeah, so there's actually a very, very nice physics that leads to this expectation. It's not simply flat band ferromagnetism. That's why I put this in quotes. So the real reason why this is true is because the band has some Berry curvature, which we can calculate, and we've calculated it in these papers. So the presence of the Berry curvature, now in some cases it turns out the Berry curvature is such that when you integrate it, you get a Chern number, in which case it's more similar to a quantum Hall ferromagnet. But even without the Chern number, the presence of the Berry curvature leads to, when you construct one-year functions, leads to one-year functions that are fat. And then it turns out that in the strong coupling limit, there is an inter-site ferromagnetic Hund's interaction, which for W much smaller than U dominates over the super exchange.
Yeah, I'm good. Thanks.
All right, sure.
Okay, so I think in view of time, we'd better thank Senthil again here for a very, very interesting talk. So let's unmute and
thank you all. Thank you for listening.
Will you be able to join the student-led chat?
Yeah, I should be able to join for at least for a good portion of that. It's from 6 to 6:45 London time.
Yes, correct.
That's 1 to 1.